Hey everyone, welcome to today's webinar, Causality and Probabilistic Modeling in Machine Learning. I am Sam Charrington, founder of TWIML and host of the TWIML AI podcast, and I am here with Robert Osazuwa Ness, an ML research scientist and professor. Robert, say hi.
Hey Sam, hi everybody.
All right, so I'm going to jump into just a little bit of background about TWIML and the TWIML community, and then hand the reins over to Robert to introduce us to his work and new courses and the topic of causal modeling in machine learning. So first off, I want to just share a little bit about TWIML and the TWIML mission. We are all about making machine learning and AI more accessible and enriching the lives of you, our community, and our listeners by sharing and amplifying the voices of a broad and diverse spectrum of ML and AI researchers, practitioners, and innovators through our podcasts, through our programs like this one, and through our community. Our community is about 5,000 members strong now. We participate in educational programs like the ones we'll be talking about today, as well as a pretty wide variety of study groups and shared interest groups focused on things from, everything from topics like natural language processing, computer vision, deep learning and machine learning, to competing in Kaggle competitions together. There's what brings this community together is a shared interest in growing our knowledge of machine learning and AI. And again, we do it through study groups and courses like the one we'll be talking about, as well as we have a robust Slack channel. And you can access all of this at no cost by visiting twimlai.com/community to learn more and join up. I wanted to briefly mention our conference, TWIMLcon AI Platforms. We hold a couple of events each year. One is called TWIML Fest. It's a community-oriented AI festival. We just had this one in October, and this is really all about learning together and we cover a wide variety of topics. TWIMLcon AI Platforms is coming up in just about a week. January 19th is the start. And this conference is all about making machine learning productive within enterprises. So we talk about topics like ML ops and the operationalization and productionalization of machine learning models to benefit businesses and organizations that really depend on these to better serve users, grow their businesses, etc. I invite you to join us for the conference and to use the discount code CausalML for 25% off of registration. And so I told you a little bit about me. I'm Sam. You may know who I am already. I'd like to use this opportunity to turn the reins over to Robert to share a little bit about his background and dive into the topic that we came here to talk about today, causal modeling in machine learning. Robert?
Great. Thanks, Sam. I'm sharing my screen. Can you see it okay?
We've got it. Yep.
That's okay. Great. So yeah, thanks for that great introduction. And I do want to encourage folks to think about signing up for TWIMLcon. I'm going to be there, and I'm really looking forward to it. I'll actually talk a little bit about some DevOps material in this presentation. But yeah, that's a great community event. I hope we can. I hope I can find some of you there. So Sam introduced himself. Let me introduce myself. I'm a research engineer focusing on machine learning, primarily focused on causal modeling and probabilistic programming. Also working a lot these days in natural language processing and back in the day in systems biology. I work mostly in Python. I enjoy work using R and Julia. I write a lot and I teach a lot at altdeep.ai. And we're talking about some workshops that I'm a cohort of workshops that I'm running this spring through AltDeep. I'm a Purdue PhD statistician. I've published at particularly on causal inference and other machine learning topics at conferences like NeurIPS. I'm married to a computer scientist. I'm fluent in Mandarin. Love functional programming. Like hiking. That's about it. Sums me up. So in this I know Sam likes to keep these things conversational, so I'm going to give this is a slide deck I have where I give a kind of overview about the state of causal reasoning in the AI community and the kinds of causal modeling problems that machine learning engineers are trying to tackle. But I think I'm going to give you part of the presentation and then skip to the end to talk about the workshops, and then kind of open up for questions and discussion with Sam.
Yeah,
So,
and I probably should have mentioned that if you are viewing this via the TWIMLai.com site or YouTube, you'll see a chat box, and you are encouraged to place your questions or ask your questions via the chat box, and we'll try to work them into the conversation or answer them at the end.
And also, I'm working with one display today. So if Sam, if you see a question pop in and you want to interrupt me, I won't see it. So please interrupt me.
Definitely.
Awesome. So the AI community is taking on causality. We have a better articulation of the causal problems that we're working on. So we know that, for example, to understand concepts from cognitive psychology, ideas like intention, blame, regret, explanation, we need causal abstractions. And so this is a quote from Judea Pearl's book of Why, where he talks about if you have a vacuum cleaner that wakes a vacuum cleaning robot that wakes you up in the middle of the night and you tell it that this was a bad thing to do, you want it to be able to assess what actions led to this outcome and reason using a word we call counterfactually about what better outcomes could have happened had it done something else. So this is different from your typical kind of reinforcement learning type of approach where you're having to figure out what the intention of the sleeper was, what action to assign blame to. These are all ideas from CogSci that require kind of counterfactual reasoning. If you were on recently on that panel that I was on with was the great AI debates, you heard Daniel Kahneman talking about, and some other cognitive scientists on the panel talking about explanation-seeking behavior. Explanation-seeking behavior in psychology and causal modeling and machine learning are very closely related. We also needed to understand physics, so things like mechanism, time, and space. This is a quote by Gary Marcus in his book Rebooting AI, but generally the idea is that we've got to go beyond just doing very sophisticated non-linear correlation. Seeking, right? What we really need to do is have some kind of innate grasp of physics, physical concepts like time, space, and causality in order to make, for example, robots that can reason in 3D environments. Just like a child can look at something sharp and reason about its sharpness without actually having to touch it. And some of the more eminent people within the machine learning community are taking on this topic with gusto. So here's Yasha Beggio in recent years has been talking about extending deep learning to or deep learning architectures to the problem of causal induction. This was a panel at this is NeurIPS 2018. So we have some, David Bly, Yasha Bengio, Bernard Shokov, some, people you've heard of if you worked in deep learning or latent variable models, for example, but perhaps you didn't realize they were from causality. And so now you know. And also, explainability and algorithmic bias and fairness is an issue that is an area of research that is not only, of course, very impactful and very important, but it's also very interesting. These are we're hitting on some very interesting technical problems in this field, and a good chunk of those technical problems are problems that we require a causal semantics to parse. This is an image from the ProPublica article on an algorithm that was used in Florida to predict whether or not somebody who was up for parole would recommit an offense. And what they did was find people who had very similar profiles that were different except for race, and showed that the algorithm was inexplicably assigning race people who are Black with higher risk profiles. This is given the same crimes, given the same backgrounds, the same set of previous offenses, but this took a lot of work by ProPublica. They had to do a very intense analysis, a causal analysis with some using kind of, say for example, graph semantics would have made that analysis far easier and reproducible, and make sure that you could apply these types of reasoning approaches in future algorithms. So today I'm going to cover what a causal model is and what it can do that deep learning, at least canonical machine deep learning, cannot do. Typically with this talk, I talk a little bit about what the big tech companies are doing with causality, how you, if you're bringing to the table some existing machine learning skills, like you're really good at neural nets, or you're really good at modeling with generalized linear models in R, for example, what you can how you can build on that skill set to acquire some practical experience building causal models. That's important, I think, to some of the people in this audience, and I'm happy to talk about that if you ask questions, and point you in the direction of some tutorials. But after I talk about this first topic here, I'll skip right down to the workshops, and then we'll have a conversation with Sam. So, what is it a causal model can do, and what can it do that deep learning can't? So, to understand this, we need to understand something called the levels of causal queries. Some people call this the ladder of causality. At the top here, we have an association query. So this is given that you have some feature X equal to some value X, predict Y. So in plain English, you might say, given someone on an exercise regime, what body mass index, what BMI are they likely to have? Right. So the way you would do this is you would get a whole bunch of people who are on various exercise regimes, or people who aren't on exercise regimes, record their BMIs, and then fit a model. Right. And in these types of predictive models, deep learning is extremely powerful, because no matter how many dimensions are in X, or how nonlinear relationship it is between X and Y, deep learning is going to find a mapping. The next up, we have intervention queries. So an intervention is to say, rather than say observing X has some value, we're going to force X to take some value. So if we force someone to start taking an exercise regime, how will it affect their BMI? And this is actually the more interesting question than this, because when I'm not interested in observing, the statistical correlation between exercise and BMI. I'm interested in the question: what happens if I make myself go sign up for an exercise program at the gym? How is that going to affect my BMI? And that question is where I'm changing the system from what was observed in the training data. And that breaks traditional machine learning and deep learning, because that future data, because you've now done that new thing, differs from the training data. And so in order to do prediction under intervention requires an explicit model, in some sense, of cause and effect relationships. And finally, we have the counterfactual, more generally, something called a multiverse counterfactual, which is given some things that we've observed. So with some X and Y, what would Y have been if X had been different? So in other words, given my current BMI and the fact that I am in the gym or I'm not in the gym, what would my BMI had been had I done something different? So if I was not going to the gym and I have this BMI, what would my BMI be had I signed up for the gym last year, for example? And so this is the ultimate level of causal reasoning, because in this case, in this final case, what we're doing is we're reasoning on data that we haven't ever seen. There is no training data here because that alternate universe where you did go to the gym is not observable by your algorithm. So in order to actually model this, you need an explicit modeling of cause and effect relationships and a way to use data that you observed, namely that I went to the gym, or I didn't go to the gym rather, and I had a certain BMI, to predict what would have happened in the other universe. And we can take a generative modeling approach to these questions, right? So at each level of these queries, we can take a sampling mechanism. So a sampling scheme. So if you're into generative modeling, you know that generative modeling works by generating samples and then treating the samples as samples from a distribution and then reasoning over those distributions. And so we can say, for example, here's a model of images, say in a computer vision problem of people who are boxing, of boxers, right? And so we have a node here, a graphical model representation of this model, this causal model. The edges here correspond to causality. The nodes correspond to causes and effects. And so the pixels here, that's the image that we see. And here are some of the attributes of the image, so that we have somebody they're training and they're in a training kind of pose, or they're bloodied, or they're posing. We have the gender of the individual, and then we have the ethnicity of the individual in the image. And this bar here corresponds to this is a bidirected edge, which means that there's some perhaps latent common causes between gender and ethnicity. And so if we were to sample from just the association model, what we would see is we see it be heavily skewed towards males. So this is, say, 3 samples from that model, from this model, just randomly generating from this model, because most boxers are male. Now what we can do is we can take this model and we can fix gender to being female. And what this is doing is saying, like, all right, I want gender to be female, whatever relationship, since I'm fixing gender to be female, I'm breaking whatever impact it's having, that this latent cause is having on it, because I'm fixing it. So nothing can change that, because I've gone in and I've changed the data generating process from what it was in the training data. And here, this kind of backdoor statistical association between gender and ethnicity is going to be unaffected. And so if I generate from this intervention model, I'll see only women. And then finally, in the counterfactual setting, I would actually see an image of a person. So here is an image of a white female boxer who is posing, and I might ask the question counterfactually: how would this image appear? How would these pixels render if the subject of the image were Asian? And we would sample from this image, and we would see variation in the image. We would see a variation in the image that would come from ethnicity, but everything else in the image that was specific to that has nothing to do with ethnicity is caused by other elements that are not varying, would stay the same. And the question now, of course, if you're familiar with deep learning, is, well, I've seen deep fakes, right? I know that deep learning can do this. And the answer to that is yes. But what's happening is that in order to achieve that with deep learning, either you have to curate the data set and create the features and response that are specific to that question. So you say, for example, like, all right, I want to generate this counterfactual image, and so here are a bunch of I need to go kind of hand-picked images for my model to actually get that specific query outcome. I would have to also think hard about the loss function, the training procedure. While what we want, if we have a truly causal model, is to be able to handle any causal query that we throw at it and to do so, that would require, we want to do so with less data. We don't want to have to kind of acquire a new data set every time we want to train a different query. We want it to be glitchy, right? We want it to be less glitchy because we want it to, if we're having some kind of, if there's some kind of causal representation of the abstraction behind the image, we would expect there not to be strange artifacts like we see here or here, and in these corners of this image here. And also, we can also import deep learning architectures into this approach. There's a growing abundance of literature on deep causal generative models that will allow us to take the power of deep learning techniques, especially in computer vision, while allowing us to apply principled, formally proven algorithms from causal inference theory to reason about the images in the way I just described. Interventions themselves, they're actually extremely important in machine learning driven decision making. So this is things that people are actually doing in practice, in particularly in tech companies as well as retail companies. The idea is this: let's suppose that I'm training a model. This is the first. I'm going to collect some data points on a daily basis in a block of training. Collect a block of training data, train a model, and then productionize it, deploy it, and while it's in production, it's going to collect some more data, and then I'm going to retrain at a later step. So what's going to happen is that each morning and each evening, I'm going to collect a sensor reading of the weather, say a barometer, for example. And then in the evening, I'm going to record whether or not it was sunny that day. So for example, for the first 2 days of this training block, it was sunny, then it was rainy, then it was sunny, then it was rainy. Then I train my model and I deploy it. So what it's going to do is, based on I create an app that takes in the barometer reading and predicts whether or not it's going to rain, and I'm going to use that to make a decision. Should I carry an umbrella or not? So here's what happened. That first time, the algorithm told me not to bring an umbrella. It was sunny, so I'm happy. The second time, it told me to bring an umbrella. It was rainy, so I was happy. The third time, it told me not to bring an umbrella, but it rained, so I was unhappy. Third time, it told me not to bring an umbrella. It was sunny, so I was happy. Finally, it told me to bring an umbrella. It was sunny, so I'm unhappy. So the issue here is that the weather doesn't care about whether or not I brought an umbrella that day. But in other domains, the thing that I do, the thing that my algorithm tells me to do based on its prediction, could affect future data. So here we're going to duplicate it. Instead, we're going to look, instead of morning and evening barometer readings and weather, we're going to look at the start of the quarter, at revenue projections for that quarter, and then the actual revenue that quarter. Right? We record some, we train a model. Notice that this is exactly kind of mirroring the situation that we had up top. Now let's look at after we've deployed the model and see how we might use it. So I get a revenue report. It says that I should not advertise. Revenue goes up. I'm happy. But the fact that I didn't advertise affects revenue in the next quarter. And so what happens? So basically what we want to do is compare it to this situation here. So in this situation, we have something where my bringing the umbrella is not going to affect the weather the next day, but my advertising will affect revenue the next day. And this, as you can see, this is in practical settings in industry, this is a very important problem. We're creating a kind of feedback loop between the behavior that our predictive algorithm is motivating, and the data that's used to train the algorithm. So this is a problem often, for example, in detecting fraud. I train an algorithm based on I get a whole bunch of transactions. Some of them are fraudulent. And what I see is, and then I train the algorithm to predict fraud. But then I deploy that algorithm because I want to block fraudulent transactions. Now I start blocking fraudulent transactions. I get a new data set of that contains some fraudulent transactions that manage to sneak through, that manage to get under the the current state of my algorithm. And so what happens now is I'm going to bias my training algorithm. If I don't have a causal model, I'm going to bias my training algorithm to these new examples of extremely sneaky, hard to detect, and probably somewhat outlying instances of fraud. And what that could do is say let more conventional instances of fraud sneak through. Finally, we're seeing an increasing need for causal modeling in reinforcement learning and general and agent modeling in general. So reinforcement learning being a very special case of agent modeling. If you come from a reinforcement learning background, you might be squinting at this equation, thinking that it looks familiar. This is just the Bellman equation written as, so Bellman equation is a important equation in machine learning. It's, for example, where the Q and Q learning comes from. But this is it written in causal inference in causal modeling notation. So this is an intervention. We're saying that we're going to do an action according to some policy that's driven by the current state. You don't really need to understand that, but what all I'm saying here is that we can take principles from causal inference and causal modeling and apply them to the fundamentals of reinforcement learning and get some very useful outcomes out there, namely in terms of getting better policies. And in getting policies with less data. But also we want to, if you think back to that counterfactual reasoning idea that I mentioned earlier, what's really interesting about agent modeling and causality is that we want agents that can reason counterfactually, because humans reason counterfactually, and it's a very useful way of thinking. So in other words, we want an agent that can, in production, it could say, all right, look at these logs that I've generated over the last day. Based on these logs, well, you as the person who's modeling the agent, you could say, well, had we given this agent different decision-making policy, how much better would it have done? So actually, this would probably be more of a this is reasoning about an agent in production. So we're thinking, how could I have given how the performance of this agent, how could we have made it do better? How would it have done better under a different policy? And rather than actually going and implementing that policy, rather deploying an agent with that policy, you can reason using causal inferences to kind of predict how that agent would have done given data that you actually have. But you also want to give the agent this superpower. You want to say, all right, I'm the agent. I did what I thought was the best given what I knew at the time, but given what I know now, I believe I would have gotten more reward had I done action A instead of action B. So I'm going to my policy so I won't make that mistake again. Great. So that's an overview for why machine learning is important why causality is important in the context of machine learning and what problems it's being applied to. I talked about particularly the case of modeling interventions and modeling counterfactuals. Counterfactuals are, like I said, are hitting pretty heavily in the area of reinforcement learning and agent modeling. And so let me jump down just so we have time to parlay a little bit. To talking about the workshop. So this is a workshop on causal inference and causal modeling. It will give you a comprehensive introduction to causal inference, causal modeling. It'll focus on examples from artificial intelligence and machine learning and applied data science. It'll focus on it'll take a very opinionated generative machine learning approach, and it's very much focused on programmatic implementation. And so you'll be right. You'll be looking at code examples, and you'll understand how to engineer causal reasoning systems. Every week, we'll have a live review of that week's content. You can also schedule one-on-ones with me and the other instructors through a scheduling app. And there is no real limit on the amount that you can do that. You're able to schedule those meetings within the 4 months of your cohort. We'll be using a probabilistic programming deep learning library called Pyro, and we'll be using that to implement causal reasoning algorithms. And we'll focus a lot on implementation inside of when I say top tier technology organizations, I mean, if you look at, say, Netflix or Facebook, and you see what kinds of positions they are hiring for that focus on causal inference, those are the positions we're training for, and as well as I want to emphasize companies in tech-savvy marketing companies. So this is people who are doing retail, people who are analyzing customer behavior, and have developed data science teams that are functional. And the second, we're also running a course this cohort on probabilistic. It's called Probabilistic Modeler in 3 months. And so this takes some of the generative machine learning and probabilistic modeling ideas that are touched on but not gone into in depth in the causal modeling course. And in this course, we go into it much more depth. And it's similar to other, in terms of material, we're looking at probabilistic modeling and machine learning. Or alternatively Bayesian modeling, but we're focused much more on application. We're using we're also using Pyro, which is PyTorch based, and we're looking at how to build these into engineering systems. We're looking to show people the entire Bayesian modeling workflow and philosophy. So just going beyond Bayes' rule, but actually, how do I build a model from scratch? How do I check it at each level of iteration? How do I increase in complexity without breaking it? How do I put it into an ETL pipeline so that the model artifacts are being stored in a place where they can be queried and reused in the future? This course was developed with a lot of feedback from team leaders and data science teams and consultants one thing that they were observing was that people were getting really good at importing libraries and just applying them to a data set and then debugging them. And they were afraid because they felt like, well, if that's the way things are going, then we really can't add much value because these are basic skills and that are becoming commodified very quickly. So they were looking for ways of kind of building a principal modeling workflow that builds IP for the organization that accrues over time, but also skills for the modeler that you really can't just learn from a 1 hour long Medium tutorial. Also, they emphasize much on this Bayesian decision theory principles to actually tie this to business metrics and key performance indicators in the organization that you're working for. And finally, the last point I'll make here is that we're looking to learn workflows around building models that are and inference algorithms as explicit code that we can we can apply the normal to which we can apply the normal software engineering process to. And finally, there's a very heavy skew in this course on Bayesian cognitive science. So if you're coming from a view of AI and you're trying to understand, say, this new trend in neurosymbolic artificial intelligence, this is a kind of Bayesian backdoor to neurosymbolic artificial intelligence. that you can, they'll allow you to kind of, we're going to be learning how to write algorithms that can reason. So that's it. I have some, I can talk about, Sam, was there anything else that you want me to add here? I say that this is, I know you have some slides to this, Sam, but so this is, if you are, you're watching this and you're part of the TWIML community, we have a special 15% off discount for TWIML community members, and you just use this coupon code here, go TWIML 2021, when you sign up for the course, and this expires in 48 hours.
Cool. Thanks, Robert. I like to encourage folks in our audience to use this opportunity to ask your questions in whatever chat is attached to how you're watching this. One question that I've got for you, I've got a bunch of questions for you, but I think where I'll start is, we launched our collaboration around this time last year. You've since done three of these three cohorts of your courses. Last year when we were talking about this, I mentioned that, Causality, it had just seemingly out of nowhere, it had gotten very, very popular. That continues, but now we're starting to see causal ideas applied in different domains. Like the core causality is starting to mature a little bit, and now we're talking about, okay, how does it apply to reinforcement learning? I keep hearing it come up in the context of graphical models and graph deep neural networks and things like that. And I wanted to start by having you speak about the relationship between causal and graphs, and are they one and the same? Do they always complement each other? Or are they adjacent? How do you think about that?
Yeah, there's two ways. Let me say two things there. One is, so in the approach that I take in this workshop, and it's an opinionated one, is that we want to be modeling the data process explicitly. And what happens when you model the data process explicitly is that you gravitate more towards causal models. So if you actually look at probabilistic graphical models and machine learning literature, things like topic models, I guess you can take a mixture model, characterize it as a PGM, hidden Markov models. If you look to understand, because actually have a kind of causal logic to them, right? Like the latent state in the hidden Markov model causes the observed state. In a mixture model, there's some kind of latent state that switches the data from one distribution to another. There is in a topic model, the topic causes the presence or absence of a word in a document, and so so inside the causal inference literature, there's a very strong emphasis on directed acyclic graphs and as representations of causality. But of course, in the graphical modeling literature, we use DAGs as a kind of substrate for graphical models. And in this course, we combine those two. And so that makes it statistical or machine learning background. And it's also far more intuitive because you're looking at a model that represents your beliefs about the underlying system. Mm-hmm. Secondly, so you mentioned, I think you were referring to graph neural networks. Mm-hmm. And so graph neural networks are really interesting because they provide a way of encoding some inductive bias about a domain into a neural net. And think of causality as coming with its own set of inductive biases. Say, for example, without getting too technical, if there's a causal relationship between a bunch of variables, then certain properties must be true about the underlying probability distribution that connects all those variables. Say for things about conditional dependence and certain marginal probabilities being greater than other marginal probabilities. Other things that must be true are, if you were going to train this model and you were going to fit the parameters, certain sets of parameters must be independent of one another because they represent separate causal mechanisms. Those are things that a graph neural net would be very good at capturing. And so there is the reason graphs come up is because graphs are great ways to capture causal assumptions and the accompanying inductive biases that come with those assumptions.
Mm-hmm. Awesome. Got a great question in from Jesus. What would you say is the overall state of causal RL in this case? Exploration, mature. How far along are we with this relationship between causality and reinforcement learning?
Rich Sutton said that he defines reinforcement learning as both the set of methods and the problems that you're trying to solve along with those methods. And so in terms of the problem space, well, there's plenty. If you think of reinforcement learning as trying to, so let me put aside the word reinforcement learning for a second and think of, say, sequential decision, automating sequential decision making. Mm-hmm. And so plenty of people are doing that in industry, right? Like, so I'm sure that if you're getting an algorithm, if you're getting an email from a company like Netflix or Facebook, it was sent to you by an algorithm, and that algorithm will be, whether or not you receive a subsequent email will be based on whether or not you clicked on that first email, or if you clicked on it, whether or not you clicked through to whatever it is they were trying to get you to look at. And when you're designing that algorithm, it's a causal effect problem because you're trying to figure out, all right, what's the causal effect of this policy for sending emails on this ultimate outcome, which I imagine has to do with engagement in their content. And so that's very much deployed in the real world and happening. But oftentimes when we think of reinforcement learning, we think of complex action and state spaces, not just like what email to send and whether or not they clicked, but rather a video game, and you have some complex map, and you have partial information, and you have all these, and you have you have to do it has to be happening in real time and all these things. And there the impact is relatively nascent. I think right now people are focusing on simple problems just to show where it becomes useful and where it is more of a computational problem than a causal problem. Just drawing those lines itself is quite useful. I think there's a company in the Bay Area called Vicarious AI, which has published a little bit on some of these ideas. And I'd say that so I think I can share this with your community. All that needs to happen is somebody just needs to kind of show a bunch of proof of concept, causal inference, problem solving techniques on OpenAI Gym. I don't know why nobody's written that paper. I would write it if I had time. By the way, a few people who've I've already written 2 papers with previous students. I'm not promising that that's going to happen if you sign up for it, but and some of our students have gone on to write papers together. So if you're interested in research, that is one that tends to spring from these the community that grows around in these courses.
That's awesome. You mentioned some of the publications from Vicarious. Are there any other papers that come to mind on causal?
For reinforcement learning?
Yeah.
Elias Barenboim's group at Columbia University has written some interesting papers on causal reinforcement learning. I think his website is, I want to say causalai.net, maybe. He's focusing on simple proof of concept problems, but if you are if you wanted to apply those to something in OpenAI Gym, I think it'd be an easy publication.
Nice. So I mentioned that we've done several cohorts of this course. Can you talk a little bit about so the course that you've done, the first 3 cohorts had several different modules. Is one of the, how do these 2 courses here map to that course and those modules?
So when I first ran it, I broke it up into different modules. Then I decided just to combine them into one course because it was easier that way. It was just less confusing. So there's one causal machine learning course. And the interesting thing about that is that we use this probabilistic machine learning approach to it, but we stay very lightweight on the inference algorithm. So if you're familiar with Bayesian modeling, probabilistic machine learning, there's a lot of effort usually put on inference, and there's a lot of cutting stuff happen in inference. Say, for example, with approximate inference, stochastic variational inference, and causal modeling, causal inference is very much focused on the modeling aspect. And so I went, in the examples and in the tutorials and the assignments, the inference aspect is pretty basic. We just kind of structured the problem so that inference isn't hard. What happened then was I had some students who were trying to apply these things in practice and were coming back to me with general, like, all right, I have this causal model and it works and everybody in my company has buy-in, but I need to scale it up and I need to get inference to work and I need to know best practices and like model checking and, seeing if my MCMC converged or seeing if, should I use MCMC or should I use some approximate technique? And so is where this course kind of sprang from. And on top of that, we had a bunch of interest in some of the cognitive science extensions of causality, some of which I just mentioned in this talk, and which of course we didn't have time to go into because we really want to make sure that people have a solid foundation in causal inference and modeling in this course. And so that is going into this new workshop as well.
Got it. In terms of prerequisites, what are the expected backgrounds of the folks to take the 2 different workshops?
People should have a good understanding of basic probability and, nothing like, you need to know like, moment generating functions for, the gamma distribution or something, but you just like basic kind of discrete distributions, Bayes rule and conditional probability and what it means for 2 variables to be independent. And that's it.
Okay. Yeah. I think I remember someone asking about kind of background material in the community and you recommended.
Yeah, that book is super comprehensive. Like basically, I think it's like the first 17 pages of that book is what you need. But yeah, that's Sham's book, like chapter 1 on like univariate discrete probability. Not even chapter 1, like the first part of chapter 1 is like, yeah, that's all you need.
Nice. All right. So what other questions do folks have? I've got a couple of slides on the workshops, but I think they're basically the same as your slides on the workshop. But we do have the URL for folks that are interested in signing up. That can be done at twimlai.com/causal, and the codes are here. In terms of, so kind of going back to Jesus's question, we focused on kind of the status of causal RL or the status of causal RL, but what about causality in general? Like, what's your take on the level of maturity of, various aspects of causality, causal modeling, causal inference, all that stuff? I'm almost imagining like a Gartner hype cycle of, various causal things and wanting you to comment on where they are.
If you think about it, right, like these questions have been fundamental to statistics and to research for a long time, right? Like, if does smoking cause cancer, right? We know that simply observing a high cancer rate among smokers is not sufficient to conclude that, because we know correlation doesn't imply causation. And so we need we needed to develop more rigorous methods. We saw an explosion of method development in the latter half of the 20th century, particularly in the 80s and 90s. And so, like, the formal logic behind it is very sound. I'm a little bit biased because one of the things that I care about is extending this. So right now, the logic is sound, but within a very kind of narrow class of models. And I think that what the next step is to expand these principles to a broader class of models, namely, so going beyond the DAG to systems with an open amount of variables and that are perhaps Turing complete, and so you have the added expressibility of the control flow of a high-level program, and so kind of having that kind of those symbolic tools to model a system and being able to ask a new set of queries. What are those? What new things can we answer by kind of expanding out the logic of causality to, Turing complete systems? An example would be, say that you're defending, is a military example, like, you detected 5 missiles and you were able to intercept all of them. Had the enemy fired more than 11 missiles, at least one of them would have struck. Like, what's the probability that that statement is true? Right. And so that is something that's beyond the scope of, say, causal graphical models or structural causal models. But we know how to code those up. We know how to implement models that can answer that question, but we're still figuring out the theory behind them and how sound it is. So that's where I think that's for me what the frontier is.
Mm-hmm. Mm-hmm. Question in about causal discovery. Can you talk about that and where it fits in with the other concept you've mentioned, like inference and models?
So causal discovery is the task of, so you observe a whole bunch of variables and you want to discover causal relationships between them. And there is a host of algorithms that will allow you to do that. And these algorithms vary in terms of what kinds of information they can use, whether or not, how well they scale, how sensitive they are to missingness of variables. I don't cover that so much in the course, although I, wrote my dissertation on them. I think that I'm particularly excited for a combining of causal discovery and causal modeling. So it's kind of, you can think of, causal modeling is I have a causal model and I'm going to apply it. Causal discovery is what's the right causal model. And you can, of course, combine these two approaches. And I think that there are some interesting techniques coming from the machine learning community that will make that increasingly easier to do.
Mm-hmm. Anything in particular come to mind in terms of those techniques or literature that?
I'm sorry, could you repeat the beginning of the question? I didn't hear.
You mentioned that there are some techniques coming online to make causal discovery easier to do, and I'm asking if you can elaborate on that.
Yeah, I mean, I haven't actually seen anybody do it, but what it is what I've learned from deep learning researchers is that people like to say that like deep learning is all about radical imperialism. They don't want to bring in any domain knowledge. And what I've learned is that that's actually not true, that deep learning people are happy to bring in domain knowledge so long as they only have to do it once, right? Like that you specify it as some kind of model architecture that has a certain kind of inductive bias, and that inductive bias is where you capture all your domain knowledge. And so that now the data just now the inductive bias just points the inferences in the right way based on the training data. And there is a whole bunch of inductive biases that happen that causal modeling entails. I mentioned this earlier, that you could use to learn causal models from scratch, and then go beyond something what's called an equivalence class. So without getting too much into it, like previously causal models, you can only learn so much about a causal model from data, but I think we're learning new things about causal models that would allow us to actually increase the resolution that we can of zooming in, the resolution of a model a causal model that we can learn from data, and then go on to apply that model to answer queries. There isn't, I don't know of any literature of anybody doing it. There's plenty of literature of people who are actually, if you look at, so Jonas Peters has some papers on something called independence of mechanism, and which is a very useful inductive bias in causal modeling. There is Shokov and Janzing have a series of papers on trying to use independence of mechanism to learn the direction of causality. And so that's just between two nodes. So that's a causal discovery problem. But of course, scaling that up to multiple nodes is the challenge. Mm-hmm. So yeah, so look to Peters, Janzing, and Shokop for those ideas.
Cool. Last call for questions. While we're waiting for questions to come in, I guess I just want to thank you for running these courses. Again, we've done a few cohorts, and the feedback that we continue to hear is great. And I think the thing that continues to be really valuable to students beyond just kind of your teaching style and the comprehensiveness of the materials is just the degree to which you make yourself accessible to folks. And I reiterate that, to say you say that, but students who take the classes, come back time and time again and says, I can't believe that he actually makes himself this accessible to us. How is it possible for, whatever we're spending on this course for us to get so much access to Robert, and, you're serious, like, there are papers that you wrote with students and students writing papers. I mean, it's amazing to see what's come out of these courses. So thanks again for doing it.
Yeah. I mean, a conversation I had with some students last cohort is like, I don't want this to scale. Like I don't see myself getting rich off of this. I do this because I enjoy the work, and so I enjoy writing and I enjoy teaching, and so like the accessibility, the interaction is the reason I do it. So yeah, I hope you sign up and we can interact.
Yeah, I guess I'll also mention that early on in the webinar, I posted the link to our community, which is twimlai.com/community. One of the things that has grown out of Robert's courses that we've hosted there is a kind of a free and open causality paper reading group. And you're welcome to go to the community site, sign up there. That'll send you an invitation to Slack. And the what is that channel called? It's Causality Course Public, I guess. Well, no, that's not the reading.
No, that's it. That'll be the reading group. Yeah.
Okay, that's the reading group. And how's that been going?
It's good. We recently going through a series of papers, kind of connecting computational cognitive science with causality, and it's been very rewarding. And also, like, if reading papers is not really your thing, on Twitch at All Deep TV, I live streamed the paper readings. So I find that as reading papers is hard, but if you can read them together with a community, it's a little bit easier. And then we discuss it in the following meetup.
That's awesome.
Also, some live coding of some kind of on a probabilistic modeling front. So check that out.
Very cool. All right. Well, Robert, thanks so much for joining us to give us an update on causality and talk through the continued and new workshops. Again, for folks who may be interested, TWIMLAI.com/causal and TWIMLAI.com/probabilistic modeler. If you haven't already gathered, Robert is active on the Slack as well, and accessible to folks not just who are in his course, but in general. So feel free to jump on there and ask any questions you have.
Thanks, Sam. Thanks, everybody.
Thanks, everyone. Thanks, Robert.